Good morning. My name is Jack Fellows. I'm the director of the Climate Change Science Institute at Oak Ridge National Lab. For those of you who aren't familiar with the Institute, its mission is to advance the knowledge of climate change and understand its consequences. Periodically, the Institute brings in speakers from the climate research and policy community to discuss current issues in climate science and various aspects of how society will deal with the changing climate. Today, we have Dr. Katharine Hayhoe visiting us, and she has agreed to give us this seminar about her perspectives on both climate science and policy issues. Last night, Katharine spoke at an event sponsored by both the Institute and the Oak Ridge League of Women Voters. There were close to 300 people at that event, and we had a very lively question and answer session after Katharine spoke. So most of you have probably seen Dr. Hayhoe's bio. Katharine is a respected climate scientist whose research has advanced our knowledge of climate change and the use of that information to help society deal with those changes. She is a professor and director of the Climate Science Center at Texas Tech University and has a bachelor's in physics from the University of Toronto and a master's and PhD in atmospheric sciences from the University of Illinois. She has been involved in a broad range of national and international climate assessments and the author or co-author of over 100 peer-reviewed publications. Equally important, she has been a tireless speaker on the issues facing society relative to a changing climate and our responsibility to be good stewards of this planet we call home. As you saw from her bio, she also has received many awards for this effort, including Time Magazine 100's Most Influential People. And our community owes a great deal of thanks to Katharine for her willingness to serve our nation as both a researcher and a communicator. Katharine, it is my pleasure to welcome you this morning, and we're looking forward to your talk.
As Jack said, I began my career in astrophysics, and I was planning on continuing my career in astrophysics. Until finishing up my undergrad degree, I took a class, sort of accidentally. I knew what the class was about, but at least I thought I did. I didn't realize that climate modeling was the very physics and some of the actual astronomy that I had been learning for the past 4 years. I took a class by a guy called Danny Harvey who had just come back from doing a postdoc with Steve Schneider. And those of you in the climate world will know the name Steve Schneider. He's one of the early leaders in not just climate modeling, but application of that science to policy decisions. I took that class, and I realized that I serendipitously had the exact skill set that you need to go into this important field. And up until then, I hadn't really realized how all-encompassing climate change was. I had mentally lumped it with air pollution, deforestation, biodiversity loss, all of these sort of environmental issues that we need to fix and that are important. But I didn't realize that climate change is like the hole in the bucket. We're trying to fix this problem. We're pouring all of our effort, all of our funds, everything we have into this bucket to solve this problem. And climate change is that hole in the bottom that is getting bigger and bigger to the point where we won't be able to fix many of the greatest problems confronting our planet, problems of hunger, poverty, injustice, without leaving climate change out of the picture. And so at that point, I had a choice. I said, what am I going to do? I've already applied to all of the grad schools I was going to apply to. Maybe now I have to apply to a few more and see who I can find who does policy-relevant science. And so I sent out my grad applications back in the day when you had to send out money orders. I'm sure a few people still remember that. And I had gone to the bank ahead of time and gotten a certain number of money orders. Well, at the end, I had one money order left. I said, what's this going to go to? I want an atmospheric science program. I want one that does policy-relevant research. And back in those days, you know, all you had was the course catalog to go through and very rudimentary websites. So I was like, okay, there's 2 universities that seem to have good programs, Ohio State and Illinois, that I haven't applied to yet. I'd already applied to Boulder and UCLA and places like that. And I hate to admit this, but OSU had a water ski team and Illinois had a sailing club. And I enjoy both of those, but the sailing club won. And so that is where the final money order went. And unbeknownst to me, while I was sending in that money order, they were hiring a new chair for their department. a man called Don Webbles, who Jack knows well, who was not on the website and was not in the course calendar. But when my application arrived, he saw what my letter of intent and what I wanted to do. He contacted me, I met him, and that was the beginning of the rest of my career. He had just come from doing ozone assessments, working with ozone-depleting substances, looking at everything from DuPont Chemical to the EPA to the FAA to big airline companies, looking at how our actions are affecting the ozone hole, and he was turning his attention to climate change. So that was the beginning of my journey into what my talk is about today, the societal implications of our science. Because we are doing science that has a profound impact on almost every aspect of society in a far broader way than we often imagine when we first start doing our kind of narrow disciplined work. But we're confronting an enormous challenge. And the enormous challenge is not necessarily what you think it is. For those of us in the area of climate or in science in general, we are confronted with a world today where people think that science is something you can choose to believe in or not. And I talked about that last night. I asked people last night, do you believe in global warming? And the majority of people said they did. And I said, I don't. Why? Because science isn't something you believe in. My belief does not matter. Science is true whether I agree with it or not. So we're confronting a problem, and we often think it's, well, people don't believe in science, so we need to educate people as to the importance of science and the fact that it's true. The reality is everybody really does believe in science. Everybody knows that gravity is real. And in their heart of hearts, most people who are up there saying climate change isn't real or we're not sure about it, they really actually do know that it's real. And that includes most of our politicians. When we envision climate change, when we think of climate change as scientists, we often picture data. And so what do you think, if you had to pick one figure that really tells the story of how humans are affecting our planet, if you had to pick one figure, one data set, what would it be? I should have polled you, because in retrospect, this would have been a good poll. I should have polled you, but I'm willing to bet, and keep your hand there for a second, I'm willing to bet you might have thought of the healing curve, CO2 going up, or you might have thought of the NASA GISS record of global temperature, or perhaps you might have looked at paleoclimate records from ice cores. And what record did you have in mind?
Arctic ice.
Arctic sea ice. I should add that to this, yes. We often have these data sets in mind, but here's the issue. CO2 is a trace gas at 400 parts per million, which sounds extreme to us, but when you get out there in the public, people are like, oh, 400 parts per million, that's nothing. How could something so small affect something as big as our planet? Global temperature looks extreme, but if people look at the axes here and you convert it, even if you convert it to Fahrenheit, we're talking about a 1.5 degree temperature change. And there is a greater difference between the temperature in this room and the hallway outside than has happened to our planet over the past 100 years. And if you're talking about ice cores, first of all, one issue we have is about 30 to 40% of the country. If you show something going back 800,000 years, you've automatically lost them, number one. So yes, I have a figure of ice core data going back 6,000 years, and I use it frequently. Number one, there's the issue of time, and number two, there's the issue of people saying, oh, well, it's just a natural cycle anyways, and that is why I think it's so valuable to show the future scenarios in context. So you see there's problems with the iconic data sets that we as scientists firmly believe embody and envision this problem we have with our planet. And then if you ask the general public, if you were writing a book about climate change, if you were writing a school report about climate change, what's a picture you would put on the cover? Not a data set, but a photo. What would that photo be of? There is one thing that just about everybody would pick for a photo of a report on climate change or global warming. Thank you. That's exactly what it is, a polar bear, standing on a piece of melting ice. And so what message does this reinforce? It reinforces the message that it is a distant issue, that it matters to animals that very few of us have actually seen in the wild. How many people have actually seen a polar bear in the wild? Yeah, I have too, so I'm putting up my hand. See, we're scientists. right? And so, I mean, in this room, we represent far more people who've potentially seen polar bears in the wild than the average person. So this represents the idea that it's far away, it's distant in time. And if we're a little bit more tuned in, we'll see pictures maybe from Tuvalu of flooding on low-lying islands in the Pacific or the Indian Ocean. But they still seem far away. So as a general society, one of the most dangerous myths that I think we've bought into is not the myth that science isn't real, but rather, when it comes to climate change specifically, the myth that it is a distant and far away issue that only matters to future generations or to people who live far away from us. And I have data, being a scientist, I have data to reinforce this. So I showed some of this data last night. It's from the Yale Public Opinion Maps. Fascinating maps. You can play with them. You can look at congressional districts and counties. And I'm going to show you a few of them to make this point. So they asked people across the United States, do you think global warming will harm plants and animals? Anything over 50% is yellow to orange. And the darker the color, the more people say yes. Anything blue is less. So guess what? I can't find a single county in the entire country where people say global warming won't harm plants and animals. Isn't that amazing? Probably wouldn't be what you expect. Now, they ask a question, do you think global warming will harm future generations? Yes. Do you think global warming will harm people in developing countries? Yes. Now, we're starting to get a few blue counties or a few white ones, around 50%. And some of those are in Tennessee, but most people are still saying yes. Now, do you think global warming is already harming other people in the United States now or within the next 10 years? And now here's the kicker. Do you think global warming will ever harm you personally? The greatest and potentially most dangerous myth we've bought into is that this doesn't matter. And that's why during the last elections, there weren't any questions about climate change, because it just wasn't high enough up people's radar, even for people who say, sure, it's a real problem. Why do we care about a changing climate? We care about it not because of the polar bear, although polar bears are certainly vulnerable, not necessarily because of people on the other side of the world, although I care about them too. We care about it because we've built the vulnerability to climate change into the very systems in the places where we live. And I put a ... there because you can fill in whatever you want. We have built our vulnerability to a changing climate into our agricultural system. We have built it into our water planning. We've built it into our energy supply and demand. We've built it into our infrastructure, our transportation infrastructure, our buildings. We've built it into our economy. How have we done that? Well, I'll just give you one simple example. Imagine that you lived along the Gulf Coast 1,000 years ago. Imagine if sea level along the Gulf Coast rose 2, 4, 6, or even 8 feet over a matter of decades. What would you do? You would pick up your thatched hut, you would pick up your nets, and you would move them, right? Not really a big deal, especially when you're talking about changes over multiple generations. But over the last few hundred years, our world has seen an enormous change, and the majority of that change has been driven by this curve. And so today, we have 2/3 of the world's biggest cities within a few feet of sea level. You cannot pick up 2/3 of the world's biggest cities and move them over the timescales that we're talking about now, even over decadal timescales. We have almost every arable acre of land allocated, and that is not arable is currently covered in natural ecosystems. So arable land is actually on the rise because people are taking natural ecosystems and turning them into farmland. But what happens if you're a cotton farmer in West Texas? This is a picture of our backyard, basically. What happens if you're a cotton farmer in Texas and you can't grow anything on your land anymore because you're at the edge of the marginal area and the aquifer is drying up because of overuse, and precipitation patterns are getting more variable as a result of a changing climate? You can no longer just pick up your farm and move up to Kansas because somebody already owns that land. Now that gets into all kinds of issues, which we won't talk about. Guns, sovereignty, things like that. But in a civil society, you cannot do that. We already know that large portions of the world are subject to water scarcity already. There isn't enough water to go around. We already cope with poverty. The resources we have are not equally distributed. We already cope with food issues. People are dying of hunger in a world today where we burn corn in our cars, essentially. And we already struggle with disease, many of which diseases are preventable, many of which we understand, but some of which are emerging and new and we don't understand. We've built vulnerability to climate and weather into our very systems. This is NOAA's map of billion-dollar weather and climate disasters since 1980. They just updated it. This is to 2017. Texas has the most billion-dollar weather and climate events, over 90. Why are these billion-dollar events? Because we've built our infrastructure, our agriculture, our water, our urban systems such that they are adversely affected by weather and climate extremes. I talked last night a little bit about the types of things that Tennessee has experienced, everything from ice storms to floods, more floods, and even drought. Increasingly, heat waves, with headlines that it seems every year get more extreme, smothering, brutal, and the February heat wave, my personal favorite. We also see wildfires affecting us. And as those of us who study ecosystems know, wildfires are a natural part of the ecosystem. In fact, the benefits of wildfires to the natural system are often much greater than the drawbacks. So why are wildfires seen as such a negative thing? Because we have built our human habitation at the interface of the forest. And so when these fires happen now, there are financial and often human damages and costs associated with them. We're at risk of disaster. And I just finished teaching an entire class where we talked about this figure every class. It was a class on coping with natural and increasingly human-induced changes in risk. We know that our exposure is going up because we have more people. And many of those people are moving to higher exposure locations too. We know that for many of our weather and climate events, not all, but for many of them, the risk of those are going up too. Heat waves, heavy precipitation events, stronger hurricanes. So what can we do about it? This only really leaves us one option. We can certainly act to try to make that red arrow as small as we can. We can certainly act to decrease exposure, but the biggest area where we have the most potential to act is in decreasing our vulnerability. And we care about a changing climate, again, because we've built that vulnerability into our systems. Now, part of that is unavoidable just because we have as many people as we have. But we've also set up our planning processes such that they are more vulnerable than they have to be. The example that I like to use is an example from where I live. This is where I live. It's very flat. In fact, in Texas, in this part of Texas, we have upside down mountains. You're literally driving along, everything's totally flat, and all of a sudden the world just drops away under your feet and there's an enormous canyon. The second biggest canyon in the United States, Palo Duro Canyon, is just an hour and a half north of Lubbock, and I actually live in a canyon myself. It's very handy when the dust storms sweep over. One of the characteristics of such a flat landscape is that the roads are incredibly straight. They're so straight that you can drive along some of these roads, and you could stay on the road in your lane safely if you were driving along simply looking in your rearview mirror. Why does that work? It works because the roads are straight. But just before, if you're heading up I-27, just before you get to the next city, Plainview, there's a giant curve in the road, and this is literally what it looks like. There's this huge curve with these concrete silos, and if we are driving along looking backwards at the past, and there's a curve in the road, we are going to end up in the wrong place. We could be driving along as carefully as we can, looking in that rearview mirror as intently as we can, but if the path behind us is straight, we will end up off the road into that overpass. In the same way, planning for the future based on the past is like driving down the road looking in the rearview mirror. It works great when climate is stable or changing very slowly. But if it is changing rapidly, if we do not take our eyes off the past, not that the past doesn't have valuable information, it does. The past has invaluable information. But if we do not incorporate future change, we're going to end up in the wrong place, and that's where this figure comes in. We are confronting a heck of a curve in the road. So at this point, we have three choices. Mitigation, reducing our emissions, reducing the magnitude of our impact on the planet. Adaptation, preparing for a very different future, preparing for that curve in the road, slowing down, looking forwards. And suffering, which is not a sciencey word. IPCC has three working groups: the science, the adaptation, and the mitigation. There is no working group for suffering. Yet, when I went to Paris, I got to go to COP the year before last. The majority of people there were confronting this exact question. We're going to do some of each. The question is what the mix will be, because the more we reduce our emissions, the less we have to adapt and the less suffering there will be. But in Paris, the majority of the people in Paris, the majority of the countries in Paris, had little to no mitigation to do. They were there to talk adaptation or suffering. And that opened my eyes to the fact that our first world problems are very different. I was already very familiar with adaptation and with suffering because when I was 9 years old, we moved down to Colombia. And there's nothing like experiencing firsthand the impact of devastating events, from heavy rainfalls and landslides to earthquakes and volcanic eruptions. It's a very different world when you don't have the National Guard on speed dial, when you don't have insurance to rebuild your home, when you don't even have reliable warning systems to get out of the way. We take so much for granted, and the majority of the world is confronting this exact question, and they don't actually have three choices, they have two choices. So how do we characterize that curve in the road? And you might be saying, part one, oh my gosh, don't worry, it goes fast. How do we characterize that curve in the road in a way that is robust, that actually takes into account the uncertainty in future projections? The biggest thing I've learned is, as climate scientists, we often wring our hands over how do we communicate uncertainty to people. And newsflash, every single human on this planet copes with uncertainty all the time, right? We cope with uncertainty in whether we buy insurance or not, right? In health risks, in assessing the risks of other choices that we make. We cope with uncertainty all the time. And I've found, working with stakeholders, that if you're just totally upfront, you say, hey, this is the uncertainty we're coping with, and here's where it comes from. How do you deal with uncertainty? And I listen to how they cope with uncertainty already, because everybody already does. We can figure out a way to make this work. What types of uncertainty are we looking at in future projections? There's four main sources of uncertainty in future projections. The first one is simple natural variability. Our system is chaotic in that it depends critically on initial conditions. And the best way to think of a climate model simulation is as a different planet in the same orbit as the Earth. So the black line here is the real Earth. This is observed temperature in Wilmington, Delaware, just as an example. And each colored line is a simulation by a different climate model, which essentially represents a different planet Earth. What do you see here? You see that natural variability is chaotic. The most extreme year in any given simulation could be any of these years. But what do we also see here? We see that the long-term trend is consistent. And this comes directly from the models. So we cope with natural variability by saying we can't predict that a heat wave is going to happen from July 18 to July 24th in 2062. We can't do that. And you might say, well, that sounds ridiculous. Who would think that? Well, a couple of years ago, the UK put out a set of hourly stream flow projections going through the end of the century. And, you know, I work with hourly projections. You look at the statistical properties, you look at the mean, you look at the distribution, you look at the percentiles, you look at the 1 in 20-year event, 1 in 50-year event. What did people do? Oh my goodness, there's going to be a flood. in 2018 at 3 a.m., we better get ready for this flood. That's not the way we work with projections, and that's why it's so important to talk about the fact that these are climate projections over climate timescales, and we can look at the statistical properties of the distribution, but we can't get information out by hour, by day, or even by year. That's uncertainty number one. What's uncertainty number two? It's the fact that the models we work with are imperfect. And nobody is more aware of that than those of us who actually work with the models, right? I spend about a third of my time, research-wise, literally kicking the tires on the models, trying to figure out where they fall apart. That's my goal, is to figure out where they fail. Because until I figure out where they fail, I can't figure out where they succeed. So they can fail in that we don't include all the important processes, or if we do include them, we know that they're not correctly represented. And one of the biggest ones is ice sheet melt, which contributes directly to sea level rise. We also know that our models are imperfect because at spatial scales, anywhere from 20 kilometers up to 500 kilometers, we're trying to represent microphysical properties of soil and clouds and air turbulence. How can you represent something that happens at a scale like this in a model that operates with grid cells that are tens of kilometers long? That's pretty tough. So this is an important source of uncertainty, and that's what a lot of experiments, including many done right here, are devoted to. Our third source of uncertainty is that we've never conducted an experiment with our planet of this magnitude. So when we kick the planet, how will it respond? This is something called climate sensitivity. It's formally defined as the temperature change resulting from a doubling of carbon dioxide levels in the atmosphere. It's a probability distribution function with an alarmingly long fat tail, a median value of around 2.5 to 3 degrees Celsius these days. It kind of goes back and forth between 2.5 and 3, depending on when. This is a bit of an older plot. But I don't want to use the word scared. What concerned me the most, the more I learned about paleoclimate, was the fact that if you look back at the last episode of Most Abrupt Change, which was about 66 million years ago, the estimated emission rate of carbon dioxide to the atmosphere, from natural sources obviously back then, the estimated emission rate was about 1/10 the rate today. And so Bob Kopp and I just wrote an article recently in Environmental Research Letters called What Surprises Does the Climate System Hold? And in that we talk about, it's open access, so you can get it for free. In that we talk about specifically, we've never seen our planet being pushed this fast, this far. And so it is uncertain exactly how our planet's going to respond. But then we have uncertainty number 4. And that is the fact that our choices will determine future change. Will we reduce our emissions? Actually pretty quickly by transitioning rapidly to clean energy. Will we continue on our current pathway? And the million-dollar question here is, which scenario is most likely? I cannot tell you how many times everybody from researchers to stakeholders have said, just give me the most likely scenario. Because there's a whole bunch in the middle there too, and there's even ones below that now. Just give me the most likely scenario. And the only thing I can say is this. You know who the bottom one is? Miss Cleo? So we lived in South Bend, Indiana for 5 years. My husband was at Notre Dame, and we had an interesting experience, many interesting experiences actually. One of the most interesting experiences was the time I opened our local phone bill, not the long distance one, the local one, and there was over $1,000 worth of calls to Miss Cleo on our phone line. Turns out Miss Cleo charges $10 a minute. It turns out Miss Cleo also records the first 30 seconds of each conversation. And the first thing she does is she says, hello, what's your name? And who knew the person actually said their real name? As they were, and I'm not joking, as they had climbed up a telephone pole on special spiked shoes at 3 in the morning to shave off the insulation on our phone line and tap into it to call Miss Cleo. True story. We found out who it was. It was Shandell Talbert. I still remember her name. Shandell moved out soon after that. MCI was trying to recover their costs. All that to say, unless you are one of these two people, don't try to pick the most likely scenario, because the most likely scenario is not the middle. We as physical scientists, we know that physical data, the uncertainty in physical data often follows a normal distribution, right? So the middle of the distribution is much more likely than the tails. But you could argue for this to actually be a bimodal distribution. Either we do something or we don't do something about climate change. If you pinned me down and you tried to force me to pick which is the most likely scenario, I would say our most likely scenario is we're actually starting to transition off the fossil-intensive scenario, not really thanks to the United States, mostly thanks to China with some assistance from India. We're starting to slowly transition off the higher scenario, but nowhere near the green scenario yet, and certainly nowhere near the lower scenarios we're talking about these days. So if I had to put money on it, I would put money on kind of slowly, gradually transitioning about 20% below the higher scenario until there was a global collective oh shit moment when the impacts of climate change became so expensive and so obvious and in your face that everybody was like, oh my goodness, we have to fix this thing now. And then emissions all of a sudden take this abrupt dive down, which is no scenario that we do with any of our climate models. So there you go. So at this point, you're saying, all right, well, how the heck do you cope with these uncertainties, right? And when we're working with people who actually need this information, I think the place to start is not with what we know, but with what they know. They know more than anybody else how climate change affects them and what they care about. So when I was working with the city of Chicago, one of the first cities I started working with, and I've had the pleasure of working with a whole range of cities now, from tiny little cities like Miami, Oklahoma, which spells it the same way as Miami, but it's called Miami. Don't ask. I did, but I'd never got an answer. So working with Miami, where most people think climate isn't changing, but they're still willing to, talk about historical trends as long as we don't call it climate change, to working with Boulder, which was very interesting because you have a very informed people, almost over-informed and almost too informed sometimes of things that aren't necessarily the case, and then working with big cities like Washington, D.C. and Austin and Chicago. So sitting down with Chicago, the first thing we said when we were locked in a room with the city departments with bag lunches is, what do you care about? And what do you think one of the first things out of their mouths was? Yes. Elections in Chicago are won or lost over potholes. Okay, who has ever driven I-94 in Chicago? You have, yes. Have you driven over a pothole? Leave your hand up. Yes, yes, right. They care about potholes. They also care about the fact that when temperature gets over about 93 or 94 degrees, their metro rails start to warp and they have to shut down some of the metro system and bus people. People care about infrastructure limits. They care about rapid snowmelt and flooding. So step one is to say, what do you care about? You tell me, what do you care about? And in one project, we were working with the Forest Service, and they said, we care about ice storms. And I said, well, we can't say anything about ice storms. So for $5,000, we assessed the literature, one master's thesis, one peer-reviewed article, and we said, we can't tell you what's going to really happen to ice storms in the Northeast, but you know what? With that, we wrote a big NSF grant together. And now we actually have an amazing algorithm that can actually detect ice storms in reanalysis data and in GCM output as well. Step two is to connect the dots. What issue is potholes related to? It's related to how often temperature crosses the freeze-thaw barrier. What issue is flooding related to? It completely depends on where you live. Do you live in Houston? Do you live in Boulder? Do you live in Nashville or Knoxville? Flooding completely depends on different types of weather systems depending on where you live. And for some cases, we can actually stop right here because we know enough about the vulnerability of the system, and we know the fact that certain things like tornadoes in Moore, Oklahoma are not going away. Can I predict, can I project, can I estimate changes in tornado frequency in Moore, Oklahoma? No. Can I tell you with about 99.9% uncertainty that they're not going away? Yes, right? So at some points, we do know enough to build resilience into our systems because we know what risks we already face today. In some cases, though, we need to know a little bit more. We want to know, is it going up or is it going down? And there, we have information to draw on. much more information than we actually think we have. So, for example, we have high confidence, and the reason why we have high confidence in this list is because it's standing on a four-legged stool. It's standing on the four-legged stool of there are observed historical trends that climate models are able to reproduce, that make sense from basic physics, and that are projected to continue in the future. That's a very robust trend. What types of things do we have high confidence in? Extreme heat going up, extreme cold going down, although there is the whole thing with the polar vortex and the changes in the jet stream due to the temperature gradient between the Arctic and the mid-latitudes. So in certain places, extreme cold I would actually put in the next category, on the next slide. In certain areas, risk of flood, like the Northeast specifically, and also Houston. Why is the risk of flood increasing in Houston? Two reasons. Heavy precipitation has increased, but what else has increased? Impervious surfaces. They pave every single piece of land you can lay your eyes on. Strongest hurricanes, severity of drought. Moderate confidence. Why moderate confidence? We have some formal detection and attribution studies that show the fingerprint of human change. In what? More intense mid-latitude storms, stronger storm surges, larger area burned by wildfire, not more wildfires, larger area burned, and increasingly at the cutting edge, we have our extreme event attribution. But then the jury is still out. We've got preliminary studies, we absolutely do. So we have things to say, things to talk about severe winters in the jet stream, changes in hurricane frequency might be going down, changes in small-scale events, work like people like Jeff Trapp are doing on supercell thunderstorms and convective activity. We have information we can draw on. We have journal articles like the one we published a couple of years ago, looking at climate extremes in the US. We have special reports, like this IPCC report on extremes. So often we have the information we need. But there are some times that we do need the quantitative information, and that's where much of my research focuses. Evaluating global climate models, do they produce the dynamical patterns that bring, say, drought to Texas? It turns out, fascinatingly, that no climate model is perfect when it comes to simulating precipitation over Texas. We're in a very interesting area caught between the Southwest and the Southeast, and some climate models give us a too strong midsummer drought. Other climate models give us a too weak midsummer drought. It's like Goldilocks, the porridge is too hot or too cold. There's really no model that gets it exactly right. And when you look at projections in annual average precipitation, you see that there is a difference between models that simulate the dynamics correctly and models that don't, in terms of the upper air pressure systems and the lower level jet that brings moisture into the region. But the fascinating thing we found, for example, for Texas, when we kicked the tires of every single CMIP 5 model out there, is that every single model shows drier conditions in the summer, more frequent drought years, and those more frequent drought years are associated with a more intense lower level jet and a longer lasting and stronger upper level high pressure system that are characteristic of dry years in the historical period. That's pretty amazing. So that's one case where we kicked the tires, and that's what we found. And then, as I'm going to talk about this afternoon in more detail, we do a lot of downscaling, which is combining observational data, high-resolution models, and big core-scale global models to get fine-scale information. What type of fine-scale information are we looking for? Boston Logan Airport. They wanted to know how often is the surface of our runways going to reach the melting point? Just picture that in your head. They want to know how frequently temperature would reach the point, not at 2 meters, but at the surface. So the first thing we said is, well, do you have surface measurements? And they did. So we had to actually do a double downscaling to the weather station at the airport and then from the weather station to the runway. And we had good news for them. Even though projected increase in extreme heat goes up, this is looking at days over 95 degrees, for example. Even though these changes go up, the black line is the actual observed, days over 95 degrees per year. And then the red shaded area is under a higher future scenario. The orange shaded area is under a lower future scenario. The range represents all the different models. So that's the uncertainty due to natural variability. And then the thick line represents the average of all of the models. That's the long-term trend. So even though there's significant increases in extreme heat days, for Boston Logan Airport, we found that no, they didn't have to be worried about melting over the next few decades. In Arizona, they did have to be worried about takeoff, because when it's too hot, the air isn't dense enough, and they have to shut down a lot of their takeoffs. Working with Austin Water. Austin Water, they didn't want temperature and precipitation. They wanted stream flow. And they didn't just want stream flow. They wanted stream flow at specific gauges. And they wanted it in a specific format, of course, because it was going into the water availability model for the state of Texas, which the state is only using to look backwards down the road, but the city of Austin wanted to use to look forwards. So we downscaled to the weather stations at the gauges, but then we had to figure out to what extent can temperature and precipitation be used to actually predict historical stream flow. And then can we actually generate a statistical model to actually create stream flow at the specific gauges, because they didn't want the gridded area models, because that wasn't the way they were set up to deal with data. And fascinatingly, we found that you could. This is one of my favorite figures. This is a probability distribution of stream flow at two different gauges that they're using in their water availability model. The black line is the actual observed stream flow. And then the blue lines, the thin blue lines are individual simulations. The thick blue line is the average of all the simulations. The blue lines are simulated stream flow from a global climate model predicting stream flow using nothing but temperature and precipitation. If that isn't amazing, I don't know what is, because there's a lot more that goes into stream flow than just that. And we use a lot of permutations and time horizons and different indices and extremes. So what's the orange? You could probably guess. The orange is future. Individual simulations, and the thick line is the average. What's happening? The shape is changing. It's getting more skewed to the dry side, and the average is changing too. But this is put in a way that they can actually put directly into their models, and they can estimate what's going to happen. So what does this look like? What does adaptation look like? In Chicago, working with Chicago, what did they do after we gave them this information? They identified their risks, one of which here was flooding. They identified their risks, and they incorporated them into their planning. 14 out of the 18 departments we worked with found ways they were already being affected by climate and weather, and ways that we could develop quantitative information. We ended up developing over 100 indices that were used by a risk management company to estimate economic costs. Not just on potholes, not just on the metro trains, but even the Department of Emergency Services. It turns out they staff the south side of Chicago by the thermometer. Why? Because we humans, our physiology, we respond in a very negative way to extreme heat. If we're sick, we get sicker. If we're not in a good mood, we get angrier. We do. Violence, crimes, assaults, emergency calls, they go up during heat waves. So we were actually able to develop some of that information for them. One of the biggest things they care about in Chicago is combined sewer overflows. And the red line shows where that has happened. And they were absolutely petrified at the idea that the Chicago River, which has been engineered to flow backwards, did you know that? The Chicago River used to flow into Lake Michigan. They have engineered it to flow backwards into the Illinois system. Why? Because then they can circumvent the pollution controls related to the Joint Commission on the Great Lakes, which is an international agreement with Canada. So they were petrified that the river would start to flow the normal way, again, because it would be flowing into the lake, which is connected to Canada, which would violate the Joint Commission agreement. So luckily, they knew at exactly what threshold they have these types of overflows, so we could calculate to within 1/10 of an inch how these would be projected to change. And obviously, there's uncertainty, and usually when I show this, I have our bars and whiskers on this too. But we gave them this information, and then 5 years later, I was speaking at a transportation research conference. And I wanted to show these examples, but I didn't know what they'd done with it. So I Googled, of course, that's what you do, right? I Googled, and that exact week, September 2015, I found these two stories. New sewers quickly dispatch heavy rains, and massive new reservoir to help alleviate Chicago area flooding. Is that cool or what? Now, you have to recognize, though, they had a bit of extra incentive because the year before this, Farmers Insurance had sued the city of Chicago for failing to adequately prepare for the impacts of a changing climate on heavy precipitation. And the terrible thing is the city couldn't say they didn't know because they did. I told them. But they're also doing all kinds of other adaptation. We looked at the urban heat island effect and how extreme heat days would increase. They're putting in green roofs to actually lower their urban heat island effect by the amount that climate change is pushing it up. They are altering their microclimate, and they have the ability to do it. Isn't that amazing? So that's what adaptation can look like. What can mitigation look like? I'm going to give you two different examples. What does it look like in Texas? Texas, with California, is the state that has the highest greenhouse gas emissions of any state. So you might say, well, clearly Texas, oil and gas, is not going to be doing mitigation. But they are. The largest army base in the US just switched to solar and wind energy because they could save money. So far this year, we're running 24% of our electricity from wind in Texas. That's what mitigation looks like. Entire towns are going green to save money. And what about China? Well, if you watch the headlines, you've probably seen headlines like this. China's shutting down over 100 coal plants, some of which are only half built. They're investing $360 billion in mitigation. Why? Why are they doing this? Because number one, when the world went to Paris, the world realized it would be more expensive not to fix this problem than it would be to fix it. And number two, that this is actually a way to supply energy, clean energy, that doesn't pollute our air or our water, to the over 1 billion people in this world who currently don't have energy, who live in energy poverty. So mitigation wears many faces. It looks like everything from Elon Musk's solar shingles. You know, you can sign up for those now. It looks like everything from his high-tech solar shingles to a solar panel on a thatched roof hut in Africa. It looks like everything from high-tech cars that you can plug in to simple light bulbs. Mitigation wears many faces today. But lastly, what does suffering look like? If we look at what countries in the world are most vulnerable to what we're doing, those are just about the exact opposite from where the carbon emissions are coming from. In fact, I have a map, I don't have it here, I have a map that I made using Tom's data, using the carbon dioxide emissions right here from Oak Ridges. And when you make that map, basically it's the exact opposite. You just flip the colors and you're pretty much done. What do these impacts look like? On the East Coast, it looks like the devastating flooding that followed Sandy. Was Sandy a natural event? Yes. Was it modified by a changing climate? Was it exacerbated? Yes. There's some areas that were flooded today that would not have been flooded 100 years ago due to sea level rise, due to warming oceans, and potentially even due to changes in the pathway of the event. What does it look like in the Arctic? It looks like nearly 200 Native American villages at imminent risk. At imminent risk according to who? According to the Army Corps of Engineers. What does it look like in the global south? What does it look like in the Middle East, where the drought in Syria drove millions of farmers to abandon their land, to move into the city, skyrocketing unemployment rates, a drought that was 3 times more likely as a result of a changing climate? Suffering looks like impacts on our water availability. It looks like impacts on our food, impacts on national security, and impacts on the economy. So, as scientists, we do science, and we need to do science. But increasingly, I think we have to be aware of what our science has to say. And today, our science is informing the idea that we have 3 choices. We can mitigate, we can adapt, or we can suffer. It's too late to pick one. We're going to do some of each, and the more mitigation we do, the less adaptation will be required in potentially different countries and different places, and the less suffering there will be. I care about a changing climate because it's the hole in the bucket. We care about poverty. We care about hunger. We care about disease. We care about air quality. We care about deforestation and biodiversity loss. But if we don't patch the hole in the bucket, we aren't going to be able to fix any of these other issues. We need to plan for that curve in the road, and this is a blue sky picture of the same curve. We need to plan for that curve in the road to ensure a safe future for all of us. Because, my favorite cartoon, you've probably seen this. What if it really is a big hoax? What if 165 years of climate science are wrong? Now, never mind that we've actually done a replication study where we took 38 peer-reviewed journal articles that cast doubt on the role of humans in climate, and we actually recalculated from scratch every single one of those articles. And we found an error in every single one of those articles, that when that error was corrected, actually brought it in line with scientific consensus. Never mind that. What if it is a big hoax? What are the terrible consequences of these choices? Livable cities. Green jobs. We have 30,000 wind energy jobs in Texas. When oil prices dropped and out-of-work oil patch workers were struggling to find somewhere to work to pay their families, many of them were taken in by a company in San Antonio who retrained them to do solar panel installations. Green jobs, sustainability, energy independence, clean water, clean air, and a safer world. Thank you. So if you have to be somewhere, you got 4 minutes to get there. Now's a good time to leave. But if you want to stay around, we have more time. We can talk, we can have questions, we can have discussion, you can comment, reflect, have at it. So let's just give people a minute to leave. And if you're way at the back, if you want to move forward, please feel free. There's going to be plenty of seats, and that way you can engage more easily. In fact, if you are way at the back, please do move forward because it'll be easier. I can kind of sit here and we can chat as opposed to like standing up at the podium. So do feel free to move forward if you're sitting in the back half. All right, I wasn't kidding. This is going to be comfortable. So if you can't see my face, now's the time to move up. All right, we have the first brave question right over there.
Yeah.
Or comment.
Oh, it's a question. So I'm a nuclear engineer, so I have to deal with constantly talking to someone who might be anti-nuclear power, and having to give them like the 30-second or maybe the 2 elevator speech saying, yeah, nuclear power plants aren't supposed to explode like a bomb or something. So what is your speech to when you meet like someone who doesn't believe in climate change in an elevator or something? How do you convince them that climate change is real?
So I actually have an elevator speech that is on YouTube. It's literally called the elevator speech. You can watch it if you want. Interestingly, my goal is not necessarily to convince people the science is real. My goal is to convince them that we can agree on a solution. And if they agree on a solution for a completely different reason, that is totally fine with me. Now, it wasn't easy to get to that point because as a scientist, I naturally feel like I could convince them, right? And we feel that way. And many people we can, usually not in an elevator, but some people we just never can convince. So my goal is to convince them that there's solutions. And so what I would do if I had 30 seconds with somebody is, first of all, I would build that bridge. I would start the conversation by saying, hey, I heard that you care about X, and I do too. This is, insert small anecdote. Then I would say, I'm really concerned, speaking from the heart. I'm concerned about our shared, we care about water. Hey, I'm from Texas, you're from Texas. Man, that was a crazy drought we just went through. I'm really concerned about our droughts because, we get them regularly. So I'm acknowledging there what they're already going to say to me. You get them regularly. We get them regularly. It's part of our natural climate. But as it gets hotter, they're getting stronger. Don't you think it makes sense to insert solution? And you can do this with nuclear energy. You can do this with wind or solar. You can do this with energy conservation. You can do this with livable cities, almost anything. And it really helps, too, when you insert solution, if you have a specific example you can actually give. So, man, our cities are expanding incredibly. Every time you turn around, there's another 1 million people and 1 million cars on the road. Did you know that making our cities green actually improves our quality of life and saves money? Dallas, LEED certified its buildings as kind of, I don't want to call it greenwashing. It wasn't greenwashing. It was just, to make themselves more attractive to, young professionals. And they ended up saving so much money, they upped their LEED certification because they could save a heck of a lot of money. Shouldn't we all be doing that? So that's my elevator speech. And I think you can modify it for almost anything. Cool. Other questions? And if you want more, you can look it up on YouTube. Yes, over here.
Yeah, what are the primary sinks of carbon in the environment? How quickly do they respond to change? So if you made mitigation efforts today to suddenly cut off all carbon, how many years would it take to recover?
Yes. So if humans miraculously disappeared off the planet tomorrow, and aliens came to the planet sometime in the future, they would be able to detect the human influence in the carbon cycle for something on the order of 10,000 years or more. Because carbon doesn't react in the atmosphere. So it's part of a cycle where it's put in, removed. Now, that assumes that there's no attempts to actually take it out of the atmosphere. And that's where a lot of the research is happening, some of it right here, right? Looking at ways to get that carbon dioxide either before it goes into the atmosphere, so at the smokestack of a coal-fired power plant, for example, taking that CO2 and piping it into giant bags of green algae, or storing it underground. But there's also other ways to develop chemical compounds that react specifically with carbon dioxide. And so they have artificial trees, whereas the wind blows through, there's actually a layer of material that reacts with the carbon dioxide and traps it. Or the old-fashioned way is planting trees. That takes the carbon out too. So just because it's in the atmosphere doesn't mean it has to be there forever. We're developing ways to take it out. But until we actually have a price on carbon, there is no financial incentive to do so. So that's why I'm a scientist, and I tend to steer pretty clear of making policy recommendations because I feel like that's way outside my ballpark. But I'm a human, and as a human, I look at the solutions to climate change, and I just feel like putting a price on carbon makes a lot of sense for a lot of reasons because it would actually incentivize carbon removal as well as incentivizing choices that we make as individuals while allowing us the freedom to do it. And especially in Texas, one of the big issues people have is, as one man put it in one of my presentations, he said, I agree with everything you say, but I don't want the government setting my thermostat. So there's a real issue when we talk about these mitigation solutions of enforced choices, which I think is one of the big reasons why the United States is so resistant to mitigation. So, question over here, yes, and then here.
What process do you go through to find friendly footing with most probably hostile audiences?
I never go anywhere I haven't been invited. So, yes. So I do not cold call people. I do not cold call elected representatives. If somebody says, would you please come talk to X person, I will not go unless X person actually wants to talk to me. And if I go to a group, there has to be at least someone who actually wants me there. It doesn't have to be everybody. Going to talk to petroleum engineers in Midland, Texas, I think there was about 3 people out of 300 who actually wanted me there, and the rest didn't. But it has to be somebody who is already part of that group, who brings me in and who introduces me and explains to the group why I'm there. Yeah. And so just to give you an example, before I moved to Texas, I wasn't doing a lot of outreach. I was doing stakeholder engagement. I was working with city planners and water managers and ecologists. But I wasn't doing a lot of outreach and communication. And it happened very, very organically because I started to get people asking me to come speak to their group. And the very first group I ever got asked to speak to was the League of Women Voters. In Texas, they were a little bit more open, but they were still, not quite sure about this whole climate change thing. And one of the women there was from a book club, so she asked me to come speak to the book club. And then a woman at the book club was the program director for Second Baptist Church. So they asked me to come speak to Second Baptist Church. And then I got asked to speak at a local Baptist college, which is actually the biggest Baptist college in Texas. The reason I was asked is because the dean was a retired scientist from Sandia National Labs. So I found out later, he did his research. He looked me up on the internet. He watched a couple of my talks. He ordered a copy of the book I wrote with my husband. He came down to Lubbock out of the blue and asked me to go for lunch with him I didn't know why this man, who I'd never heard of before, was asking me to go for lunch. But, he had legit credentials. I didn't think it was some weird person, so I said, sure. So we went for lunch, and he had a whole list of questions, about 17 questions for me. I did not know why. And then about 3 weeks after, I got a call saying, we would like you to come up and do a chapel service. Now, if you're not familiar with Christian colleges, the chapel service is, it's like the most carefully guarded thing because it's mandatory and it's where all the students go and it provides theological direction. I mean, it has to reflect the values of the school. So he invited me to do a chapel service. It was a big deal. And then after that, that was my first chapel service ever. A couple months later, I got another call from, I think it was from Hardin-Simmons, which is another Christian college. And the call went something like this. We've never had a scientist do a chapel service, but we heard that you did one at Wayland Baptist and it was okay. So if you're interested, the subtext being, I sort of hope you aren't. If you're interested, we're willing to have you come down and do it. So that's the way it worked. And I still get those types of calls today. And those are the ones I always accept. Because I know if I say no, they're not going to call up another climate scientist. So.
How can a city or even a state like California redesign its water system to move away from the snow melt reliance and be more resilient to droughts like in California? We saw that they have now water back, but they say it won't last because it's still relying on the Sierra Nevada for their snow melt water.
Yes.
How can a system that large start to move away from that sort of reliance?
Well, that's a question that is near and dear to my heart. Can you guys over here hear the question? Okay, good acoustics. It's near and dear to my heart because I actually did one of the first water availability studies for California back in 2003. So in 2003, we assembled, working with the Union of Concerned Scientists, which is a great organization if you haven't heard of it before. The Union of Concerned Scientists were doing a set of regional climate change impact studies by state. And they had done California back in the 90s, but they had done it just looking at ecology without any climate scientists on board. When they did the Great Lakes, that was when they brought climate scientists on board for the first time, and they realized there was actually quantitative projections you could use that were produced more recently than the 1980s. So they decided to go back to California. So they assembled this amazing team. We had Steve Schneider, who I talked about before. We had Chris Field. We had Michael Hanneman, who does a lot of the economic water modeling for the state. We had this huge team of researchers for California. And every area, agriculture, water, air quality, tourism, ecosystems, every area was going to be driven by the same set of climate projections, and we were going to include a high scenario and a low scenario. And to my knowledge, this is the first time that had been done in a comprehensive way. And like I said, it was almost 15 years ago now that we started the study. So Michael Hanneman took the CalFed model, the water availability model that they used for California, and we developed the climate projections you would need to actually put into that model, and they'd never done it before. They put the climate projections in, and it broke. It could not cope with the water availability under a higher scenario, because under the higher scenario, you'd be looking at up to 90% of the snowpack gone. Falling as rain in the winter, but there's no system set up to actually capture it. So that study, which we published in PNAS in 2003, Hayhoe et al., you can still find it today, that study actually led to a series of state assessments where they have redone the water availability model now to actually quantify that impact. And it led directly to the governor's executive order 2 years later, where he quoted from our paper saying because, and they had a bunch of becauses, and one of them was because of snowpack loss, California put in place the first mandatory greenhouse gas emission reductions of any state in the country. And when he signed it, it was Schwarzenegger who was the governor at the time. When he signed it, my California authors, I didn't ever live in California, my California authors were standing in the semicircle behind him. So first of all, the state's aware, and they've been aware for almost 15 years, and they've been planning for it for almost 15 years. But the question is, what are you going to do? You can build more reservoirs. You can definitely improve with water conservation. You can actually start monitoring water withdrawal from wells, which nobody was doing. Larry Dale at LBL was one of the first people to do that, and I've had conversations with him about how hard it is. He actually had to track farmers' electric bills. That was the only way he could keep track of how much water they're taking out of the aquifer. So you can improve efficiency. You can build reservoirs. You can look at crazy ideas like piping water from other places, which may have enough water to do that. you can start looking at these solutions, but I don't think, as far as I know, they've come up with a one-size-fits-all, because the drought really showed that these changes might not happen over long times. They might happen much sooner in extreme events. So I don't think there's an answer, but they're already looking at it, they're already on their way, and they're already very aware, both from future projections as well as from the recent drought, that their vulnerability is here and now, and the solutions need to be here and now. I mean, who knows? The Central Valley, as it warms, could end up shifting their growing period. So long term, there could be shifts to better match water availability with when they actually grow the crops. They might end up having to grow different crops so they can grow under slightly cooler temperatures when the water is available. There's things you can do, but the first thing you have to do is recognize there's that curve in the road, and they've recognized that big time, and they recognize they're already, probably a third into that curve. So, cool. Other questions? Yeah. Over here, and then Jack.
One of the questions I often get is, if country X or country Y is making so much, difference, climate change difference, and they're not doing anything, why should the U.S. do anything? Is there a good answer to that, or is there any models that kind of show, like, the U.S. is doing something, theoretically no one else is doing something?
I am struggling with that exact question right now. I got a question from, if you read Science News, you're probably familiar with Seth Bornstein. He writes for the Associated Press. He's one of their science journalists. So he's trying to write an article on, if the US pulls out of the Paris Agreement, can we still meet the 2-degree target? So if you assume every country has giant walls all the way up to the top of the troposphere, then you can make the calculations, right? But we don't. If you can also assume, and this is the harder one, if you can also assume that every country has giant economic walls, so that what we do technologically here doesn't impact other countries and vice versa, then you can also make the calculations. But the reality is that even if the US pulls out of the Paris Agreement, and the question is, would they do it permanently? My guess is no. Even if they permanently, hypothetically, pulled out of the Paris Agreement, would US emissions continue to rise? I would bet not, because the cheapest solar prices in the world are in developing countries. And so the technology flow, everybody wants cheap energy. The technology flow is going to go both ways. Could we still meet the 2-degree target? That's a tough question. And then the opposite question too, what if the biggest question over the last 10 years is, China's building a new coal-powered plant a day, so we could do everything we could and that wouldn't help. Well, the reality is that China is not doing that anymore. They're actually shutting down coal-fired power plants. And the issue is no longer, what if the US hypothetically did everything they could and nobody else did nothing, because that's not reality. Reality now is the rest of the world is moving quickly and the US is being left behind technologically. And if you carried this through long term, if you had this type of administration for a couple of decades, I think you would actually run a serious risk, and maybe you can comment on this, Jack, next when you're asking your question. We're running a serious risk of the US actually turning into a second world country, technologically speaking, because of that. So the question, I think, is actually starting to be flipped on its head because of advances. But the short answer is no, I don't think you can make those calculations. Not unless you make some assumptions that we know aren't true regarding both the economics of the situation, the technology flow of the situation, and simply the atmosphere itself. What do you think about that, Jack? And then, what's your question?
Well, you answered my question.
Oh.
Similar to this. And if I could answer that question about the technology, I'd probably be a very wealthy technologist.
Yes.
I don't know the exact answer to this. But I think at some point, unfortunately, you mentioned it earlier, that we'll probably get to a catastrophic event. And that's unfortunate that it's going to take that for people to really take this seriously. But that's probably what will happen. And there's some risk, as you say, that we as a country may be lost in this because we're just not stepping up to the plate and accepting this.
Yeah. I mean, the question many of us ask is it too late? And the answer to that is a certain amount of adaptation and a certain amount of suffering is already in the pipeline because of the long lifetime of carbon in the atmosphere. It's like you've been smoking for 3 decades. You go cold turkey today, there's still impacts that have built up over that time. But the work I do when I look at the future is I look at the difference between a higher and lower scenario, and increasingly, I look at the difference between a 1, a 2, a 3, and a 4 degree world. So I take climate projections, and you can actually calculate, using a moving window, at what point you get to a transient change of 2 or 3 or 4 degrees. And you can actually look at what the world looks like at 2 degrees versus at 3 degrees versus at 4 degrees. And the answer there is a stark and radical difference between 4 degrees, 2 degrees, and 1 degree. And when we work with stakeholders, I found enormous utility. For example, we're working with Iowa farmers. The majority of farmers in the room really weren't on board with the whole idea that humans were changing climate. But we showed them projected changes in corn yield using the models they used and were comfortable with. And we showed them those projected changes in the way that they were used to visualizing them. And we showed them not for like an RCP 8.5 or anything like that, where then you have to explain radiative forcing to a farmer. We talked about what's going to happen when the world gets warmer by 1, 1.5, 2, 2.5, and 3 degrees. And we showed them the yield curves. They came out of that process with a position for the Iowa Farm Bureau on the Paris Agreement. Because they looked at the 1.5 degrees and they said, we can adapt to 1.5 degrees. We can do it. They looked at 2 degrees and they said, this is going to be really tough. There are going to be some serious losses. They looked at 3 degrees and they said, no way. There's no way that we can cope with 3 degrees. So all that is to say, is it too late? No, it's not too late, because we can cope, especially, I'm sorry to say, we can cope in the countries that have more resources with a certain amount of change. It's the countries that don't have those resources that are most in danger. And so to me, the biggest eye-opener at Paris was the Green Climate Fund, which is developed countries paying into this Green Climate Fund to fund adaptation and mitigation projects in countries that have not contributed to carbon emissions in any significant way. We talk all about the limits that are required to meet 2 degrees or 1.5. The majority of countries in the world are talking about the Green Climate Fund and how people are not paying into it. Even Obama didn't pay into it what he said he would. And if you think $1 is going into it in the next 4 years, I think we can think again. So, yeah.
Katharine, you mentioned last night and also today about the importance of a carbon price.
Mm-hmm.
And I mean, I hear this coming up in various venues, and I'm convinced personally as well that this is a necessary mitigation pathway if we're really going to make a big dent in this problem.
Mm-hmm.
And so my question is, what do you think as scientists we can be doing that's most effective in, I mean, this is a tax, right? This is, calling it a price is one thing, but it's
Yeah.
in some ways a tax.
Oh, yeah.
There's this huge explosion of emotional pushback against that idea. But on the other hand, it's necessary, in my view, and maybe, so
Yeah.
just what do you think we can do?
So I'm Canadian, which in many ways is not that different from being American, but there is one enormous way that being Canadian is different than American. And I didn't realize this difference until my son was doing Introduction to American History in like grade 1, and so we bought some books from Barnes & Noble and started reading them together. I knew about the American Revolution, who doesn't? I had taken it in world history class, who doesn't? I did not realize until I'm reading that grade 1 level book that the entire American Revolution was based on taxation and government control. And when people talk about climate solutions, what are the 2 things you hear? Taxation and government control. It was like a light bulb went off in my head. I was like, oh, that's why there's such a problem with this issue. So you're perfectly right. Tax is about the dirtiest 4-letter word in American politics, which is so stunning to me that there have been a lot of Bush-era Republicans coming out in recent times saying that they actually like the idea. Why? Because it actually invokes the free market. It allows people to make their own choices. It isn't government control. If you're going to have 2 evils, the worser evil is government control, apparently, over taxes. So as a scientist, I'm really solution agnostic. I mean, any solution is better than no solution. We have no solution right now, pretty much. But the reason why I've become increasingly warm to the idea of a price on carbon or a tax is, number one, because you have conservatives endorsing it. You need a bipartisan solution. We're not going to move forward with a solution that doesn't have bipartisan support. It just isn't going to work in this polarized environment. They're going to keep flipping it. Whoever gets in power is just going to erase what the other person did. If you want a long-term solution, it has to be something that has agreement across the aisle, number one. Number two, they've actually had a price on carbon in British Columbia since 2007. And the Yale climate opinion people, whose maps I showed here, they have maps for Canada. They ask a lot of the same questions, but they ask a different question in Canada, which is, do you support a price or a tax on carbon? And guess what? There's one province that is over 50% across the province, and it's the province that's had that. Why? Because they now have the lowest personal income tax rates in all of Canada. If you've ever lived in Canada, you know. Yeah, exactly. You know what those personal income tax rates are like. And they also have one of the lowest corporate income tax rates in all of North America. So to me, the proof is in the pudding. I'd be happy with anything that works, but it seems like there's broad agreement, and for places that have actually had that, there's broad approval. The proof is in the pudding. They've had it for 8, 9 years. They actually like it. So is that the only solution? No. But is it a solution we can work with? I think so. And so that's why, even though I am, as most of us are, a rather relatively, activist-averse scientist, I decided to accept an invitation from Citizens Climate Lobby to serve as their science advisor. Because Citizens Climate Lobby it's a lobby, which is a scary word to us, but it's bipartisan. They work with people, and they have members from every range, from libertarian and Tea Party to all the way, I don't know what you call it, socialists, Canadians. They have people from the entire spectrum, and they're working towards a solution where they really, really want bipartisan support. And I talked last night about how there's a bipartisan climate solutions caucus in Congress where you're not allowed to join unless you have a member from the other party to join with you. So they have 38 members, half are Republican, half are Democrat. And although I would be happy with any solution that works, I specifically agreed to help them because I think it's pragmatically, logistically, one of the solutions that has the greatest chance of happening and sticking. So.
Okay, well, unfortunately, we're going to have to cut this off. Again, thanks for coming. I encourage you to check out Katharine's website and materials that she provides. She has a lot of great lectures on YouTube, too, that you might be interested in. So help me thank Katharine for her time.
Thank you. I should also say, too, in addition to my YouTube channel, where